Lesson 6.1 on chord properties. Now, let's first start with a quick review of what chords are. Back from lesson 1.6, we learned that a chord was a line segment whose endpoints lie on the circle. So, in that circle there, you can see segments AB and segment CD. Both these segments have their endpoints on the circle, therefore, both these segments are chords. Now, when studying angles inside a circle, there's one type of angle that we've worked with quite frequently called a central angle. And a central angle is an angle whose vertex is on the center of the circle. Given a circle, say circle O here, O is the center of the circle. So if we go and extend two rays beyond the ends of the circle there and label them ray OA and ray OB, and we formed ourselves an angle AOB, then AOB is a central angle because the vertex point O is on the center of the circle. On the other hand, there's another kind of angle called an inscribed angle. An inscribed angle is an angle whose vertex is on the circle and whose sides are chords of the circle. For example, if we were to go and, say, plot a point D on the circle and then extend it to rays beyond point D here, ray CD and ray DC and ray DE, then the angle formed there, angle CDE, is an inscribed angle because its vertex is on the circle, point D, and its sides, ray DC and ray DE, are chords of the circle. Therefore, angle CDE is an inscribed angle. Now, chords also have certain properties that need to be studied. And we aren't going to go and give any names to these particular properties. I'm just going to have all four of them go on down the list, and we'll just go through them one at a time. The first property is that if we have two chords in a circle that are congruent, then they determine two central angles that are congruent. Now, the expression to determine might seem a little ambiguous at the moment, so let me explain further. Let's say we're given chord AB here on the circle O. Now, if we were to just extend segments from O to points A and B, those segments there would form a central angle. Even though those segments were not there originally with the circle, by creating them, that determines a central angle. So even if a central angle is not there, given a chord, the endpoints of the chord, say C and D, if you were to extend those endpoints, extend segments from the center of the circle to those endpoints, that determines a central angle. Now let's say that we're actually given two chords, chord AB and chord CD, and that we're told that they're congruent. Given that fact, we can then conclude that the central angles formed from the center of the circle to the endpoints of each chord must be congruent. So in this particular case, then the measurement of angle AOB is equal to the measurement of angle COD. Our second property with chords is that if two chords in a circle are congruent, then their intercepted arcs are congruent. So again, going back to chord AB and chord CD, if these two chords are given as congruent, then it can be concluded that the chord AB is congruent, arc AB is congruent to arc CD. And remember, the intercepted arcs are the arcs, the portions of the circumference of the circle that exist between the two endpoints of the chord that are highlighted in blue. Now, further properties of chords. Third, if two chords in a circle are congruent, then they are equidistant from the center of the circle. So, in this particular case, when given chords AB and chord CD, both chords are equidistant from the center. And remember, the distance from a point to a line or a segment is measured along the perpendicular. So, these two particular perpendiculars drawn from the center of the circle to the chords are both congruent. Fourth property, the perpendicular from the center of the circle to a chord bisects the chord. In this particular case, these perpendiculars that we just drew not only are perpendiculars, but they are also segment bisectors. In this particular case, OF bisects AB, and likewise OG bisects CD. This concludes today's lesson.